Exponential Decay, brought to you by Pirates of the Caribbean Lego Man, just a journal soldier with a happy smile on his face. Apparently has a backpack too, or maybe he's got a messenger bag. Anyways, we're looking at exponential decay here. So we can use the same function that we used before. This P of t equals P naught e to the kt. Remember, this was for growth, and for growth, growth corresponded to a positive k value. But here, there's one quick modification. Now our k value has to be negative, and we would call k the decay factor now, or the decay rate. So this is when things, in fact, if you recall back from 5.2, our graphs look something like this when we talk about exponential decay. That is where p naught's a positive value. So it turns out in 1970, there was about 100,000 cases of polio worldwide. And then since then, this number has decayed because we have vaccines and things like that. It was a pretty terrible disease. And it decayed at an exponential rate of about 50% per year. So the question here is, at what point in time were there half as many cases of polio as there were in 1970? Now notice what we're going to do to save stuff. We're going to let t equals 0 correspond to 1970. We're going to note that our k equals negative 0.5 for that decay rate. And then here is our initial value, p0. So we're going to have p of t equals 100,000, e to the negative 0.5, and then t, note t is in time since 1970. So if we want to know when will there be half as many cases, we could put in the 50,000 equals 100,000, but when you divide 50,000 by 100,000, you get 1/2. Just like when we were talking about the doubling time, the halving time of exponential decay, you just solve this thing. So same type of problem as before. We want to take natural log of both sides. Note this ends up being negative 0.5t. On the right side, we have natural log of 1/2. By the way, if we wanted to, we could write this as natural log of 1 minus natural log of 2 equals negative 0.5t. We know what this is equal to. That's 0. And so really, this is just negative natural log of 2. So whatever. You can write it either way. It doesn't matter to me. We're going to end up with, negative natural log of 2 divided by negative 0.5, which really t equals natural log of 2 divided by 0.5 because those negatives cancel out. Well, this approximate value will give us the number of years after 1970 would take to cut our stuff in half. Now, I don't think you're going to be too surprised by it. It's 1.386 years. So approximately 1 year later, we cut it in half. Well, if you think about it, it's 50% per year, so that's what we should expect. All right, so here we're going to test this claim. Do the predictions based on this model support the claim that polio has been all but eradicated for over 20 years? Now the question is, what are they talking about? I'm going to assume this article was written in 1990 because that would be 20 years after the 1970 time frame that we've got here. So let us determine what is P of 20. Like, how many cases is that going to be? If you recall, exponential decay has a horizontal asymptote at 0. So mathematically speaking, this equation that we wrote here will never be 0. But if we can show that it's really stinking close, like 0.265, and 0.265 would round to 0 cases, then we could have shown that this is true or not true. So we're going to do 100,000 here, e to the negative 0.5 times 20, and just see what that spits out. Boy, okay, let's do it that way, but then I think there's another way we could do this. So 100,000 e to the negative 0.5 times 20, that equals 4.53999999 forever. So let's just round this to 4.54 cases. Yeah, that's all but eradicated. We could do another thing and say, when would this equal 0? But that's not going to work because we can't take natural log of 0. So, sadly, folks that don't get vaccinated have caused problems with polio. It's far from eradicated. So it's still out there. Okay, so let's talk about this halving time, the decay rate being cut in half. So here's a picture of what's going on with all this mess. And here's that same thing we talked about before. The decay rate K and the half-life T can be related by this. Recall what I showed you before. We get 1/2 equals e to the kt. Note that because this is decay rate, K has to be less than 0. We take natural log of both sides and we get natural log of 1/2 equals kt. Remember, this is negative. So I showed you that we took natural log of 1 minus natural log of 2 using the, what's that property? The quotient property. And because K is a negative value, this T would equal natural log of 2 divided by the positive of K. If we look at K being positive, that's what's happening here. So since this is decay, whatever value we're going to get for K is negative. And that's going to work everything out. So we don't even care about the initial value on these things. All we need to know is either the rate at which things are decaying or the length of time we want to look for. So we'll do one more problem looking at this. Turns out there's a lot of applications of the exponential decay, such as radiometric dating, used in the natural sciences. It turns out that data shows repeatedly that the amount of isotopes, in other words, radioactive varieties of carbon, remain remarkably constant in the atmosphere over time. So we can presume the amount of isotopes still remaining in a dead sample is a predictable fraction of the initial amount, based on how quickly the isotope radioactively decays. So since the 1950s, several of these methods have been used. So here's an example of that. The oldest human remains found in North America are entitled the Arlington Springs Man. They were found in 1959 on an island off of the California coast. Feel free to Google that and see what's going on. They were found to contain 21% of the carbon-14 expected in a living organism. So from laboratory experiments, we know that the half-life of carbon-14 is approximately 50 years. We're going to use this information to predict how long ago this man lived. So here's one of the presumptions we have to make. When this man died, he had 100% of his carbon in his body. And then a certain amount of years later, when he's discovered in 1959, he had 21% of the carbon in his body. So let's let T equals 0 correspond to 1959. Notice we're now going to get negative T values, which is totally fine. Well, let's see, we might not need that. Let's let our P naught equal 1 for 100%, and let's let our P of 1959, which we're calling 0, equal, no, let's not do T of 0 equals 1959. Let's let T of 0 equals time of death. And then P of 0, now let's go with P. Let's come back to that. We'll say P of 0 equals 1, and then we'll say P of some T equals 0.21, where this T value corresponds to 1959, whatever we're going to decide for that. So check out this half-life. We know that the half-life of this thing, so the half-life is equal to e to the k times 575 years. What this is going to give us is the decay rate, so how quickly the carbon leaves the body. So I didn't need the initial amount because we know the half-life time. That's just 1/2. So we ignore the initial amount. And then we know the length of time it took to get that. So if we go back to the shortcut here, we really know that we could use k times the half-life time equals natural log of 2, or k equals natural log of 2 divided by this half-life. But we could also just use our knowledge of solving exponential equations to solve this. We'd have natural log of 1/2 equals 5750 times k. Then we can divide both sides by 5750. So natural log of 1/2 divided by 5750 is going to give us our k value. So I'll slap this in my calculator, natural log of 1 divided by 2, all that mess divided by 5750. Remember, this value has to be negative because this is a decay rate. And so this is approximately equal to, see our scientific notation? That means 3 decimal places before that number and 1, 2, 1. Now, I am going to use this value in my calculations. I will write this value in my equations, but we don't want to round this value. We want to round the final answer. So let's write our equation. P of t equals 100% that we're corresponding to 1 times e to the negative 0.000121 times t. So this models the decay rate of carbon in this particular Arlington Springs man. So here you can see that where I was, maybe why I was struggling with this 1959 and what that t is going to represent. We're going to solve for the amount of time it took for this 100% to become this 21%. So I'm going to plug in the 0.21 equals 1 times e to the negative 0.000121 t, and we're going to note that this is going to tell us the time from the man's death up to when he was discovered in 1959, or presumably when they tested the amount of carbon in his body in 1959. Well, this one was unnecessary. We're just going to straight up take natural log of both sides right off the bat. And that, since these parts are inverses, leaves us with negative 0.00121 t. Oops, I missed a 0 in there. That's equal to natural log of 0.21. I then divide by this mess. So my t is equal to natural log of 0.21 divided by negative 0.00121. Now recall that I'm going to use this value in my calculator, not this approximation. So this is approximately equal to, and here's the nice thing about these TI-89 calculators, you could also do this in Desmos. You're going to hit natural log of 0.21, and then I'm going to divide by the previous answer that I've left in my calculator. If you're wondering how I did that, I hit second negative sign for ANS, for answer, and I get, well, in 1959, this guy was 12,946.35 years old. In other words, he died this many years ago. Now, if we want to know his age now in 2020, we would have to figure out, well, what's 1959 minus 2020? I should know that. Don't laugh at me too much. That was 61 years. So we really need to add 61 years to this amount to get the age of the guy from today. But, I mean, who cares? We could just count backwards from 1959 to 12,946. I'm not even going to try to bother with that. I would let Google figure that out for me, because we'd have to start messing with the whole AD stuff and BC stuff, or BCE, and all those different things, and decide whose calendar do we want to use, the Roman or the Mayan or the Jewish calendar, to try to figure out, like, at what year did this guy die. At any rate, this was how we put all this mess together. By all means, if this is confusing, let's talk about it in class on Monday. Ooh, wrong button.